Hello Adsorption Academy friends, I hope you're doing well. Welcome to our very first masterclass. I'm Mohammed, the founder of Adsorption Academy, and I'm delighted to be your host today. First of all, I want to thank you for the great support you've given to the channel and for the kind messages I have been receiving from you. I also truly appreciate your attention and participation in our very first masterclass. In this masterclass, we had participants from many countries around the world, such as the United States, China, Russia, Belgium, Australia, the Netherlands, and many other countries. We will continue our YouTube channel activities as before and share new topics with you. In addition, we plan to organize a number of other events, some online and some offline. Among these events are masterclasses, where each time we dive deep into a specific topic. In these sessions, we examine more complex cases, discuss key challenges, and highlight both the opportunities and obstacles within the field. This particular masterclass focuses on hydrogen purification using adsorption. By the end of this masterclass, we want you to be able to answer these questions. First, why is hydrogen purification important? What challenges and opportunities does it present? What methods are available for hydrogen purification, and when is adsorption method used? How can we simulate an industrial-scale hydrogen purification unit in Aspen adsorption, and what challenges might we face during simulation? And how can we address these challenges effectively? Additionally, we will explore practical tips and tricks to make simulation easier and reduce errors. Finally, we will discuss the key parameters involved in designing or modifying a hydrogen purification system, as well as the effect of each parameter on performance indicators such as hydrogen purity, recovery, and specific energy consumption. So we'll start with a preface on the importance of hydrogen purification and its applications. Then we'll define our case study and implement it in Aspen adsorption. We'll also discuss custom isotherms and how to add one to your simulation. After that, we'll present the simulation results and examine them in detail. Finally, we'll discuss the design parameters in depth and wrap up with a conclusion. To begin, let's explore why hydrogen matters in the first place. Hydrogen is a versatile and clean fuel, and it is also abundant in nature. It can be used as a fuel, a source of heat, or as a feedstock in various industries. Because of this, hydrogen can play a key role in decarbonization of many sectors, especially those where reducing emissions is especially challenging, such as the steel and cement industries. As you know, addressing climate change is one of humanity's most urgent needs, and it has been framed as the net zero emissions goal. It is estimated that by 2050, all countries will take action toward achieving this target. According to the IEA report, replacing fossil fuels with hydrogen in sectors where electrification is difficult, such as the steel and coal industries, or using hydrogen as a fuel in ships and aircraft, is a key strategy that has been highlighted. By 2050, the use of hydrogen in various sectors such as buildings, industry, transportation, electricity, and others is expected to increase significantly. This highlights the strong opportunities in this field, both in academia and industry, and shows that hydrogen decarbonization will remain an area of active work for many years to come. As we mentioned, hydrogen plays an important role as a feedstock in many industrial processes. It can react with CO2 to produce formic acid, methanol, or methane, and with nitrogen to produce ammonia through the well-known Haber-Bosch process. Hydrogen can also be stored by liquefaction or in compounds known as liquid organic hydrogen carriers, or LOHC. These carriers can store hydrogen in different forms and later release it again through dehydrogenation. Therefore, in industry, hydrogen plays an important role as a feedstock, and its purification is an essential process. Here are two examples of hydrogen applications in transportation. On the left is a car designed by Toyota, powered by hydrogen fuel, which was built in 2014. On the right is the first ship operating with liquid hydrogen and Ballard fuel cells, launched in 2023. Today, these efforts continue, and we are seeing the replacement of fossil fuels with hydrogen in airlines, trains, and many other modes of transportation. Now that we understand hydrogen's importance, let's look at how it is produced. There are several production methods, and hydrogen is named according to the method used. For example, hydrogen produced by electrolysis is called green hydrogen, while methods that emit CO2 are classified as gray or blue hydrogen, depending on whether the CO2 is captured. The most common method is steam methane reforming, or SMR, which accounts for more than 80% of global hydrogen production. SMR has a relatively high conversion rate and remains economically viable. Natural gas reacts with steam in reformers to produce hydrogen and CO2. If CO2 is captured and stored using carbon capture and storage or CCS, the product is called blue hydrogen. If CO2 is released to the atmosphere, it is gray hydrogen. To avoid pollution and reduce greenhouse gas emissions, CCS is increasingly considered. So carbon management should be an integral part of any work in this field. Here we compared the specification of hydrogen produced by steam methane reforming with other production routes. Depending on the production method, hydrogen product can differ in pressure, hydrogen content, and impurity profile. The dominant SMR route typically delivers gas at about 3 to 25 bar, 70 to 80% hydrogen, and contains impurities such as CH4, CO, N2, and CO2, with CO2 usually being the main impurity. Next, we need to determine how much purification is required for hydrogen produced by an SMR unit or supplied from other sources. The required purity depends on the intended end use. For instance, PEM fuel cells typically require very high purity, greater than 99.97%, because even a few ppm of carbon monoxide can poison the catalyst. In the semiconductor industry, purity requirements are even stricter. Trace impurities that are acceptable elsewhere can be unacceptable there. By contrast, when hydrogen is used simply for heat, the specifications are much looser. The main concern is avoiding any contaminants that would reduce combustion efficiency or damage equipment. We now look at the main methods for hydrogen purification and how they differ. The three common methods are PSA, membranes, and cryogenic separation. Each method has different requirements for the hydrogen content of the feed. For example, PSA typically performs best when the feed contains roughly 75 to 90% hydrogen. Why does PSA need higher hydrogen content in its feed? In PSA, there is always a trade-off between product purity and hydrogen recovery. Increasing purity usually reduces recovery, and we will discuss this in more detail in this masterclass. If the feed already contains a high purity of hydrogen, it is easier to achieve high product purity without losing too much recovery. But if the feed has less hydrogen, reaching very high purity while keeping acceptable recovery becomes much more difficult. Feed pressure and product flow requirements vary between these methods, and the values shown in the tables are only approximate, and in practice they can be somewhat higher or lower. In general, membrane systems are not economical for very high flow rates, while PSA is suitable across a wide range of plant sizes, from small units to fairly large installations. Another key difference is achievable product purity. PSA can deliver very high purities of up to about 99.9%, while cryogenic plants typically reach around 98%. And membrane systems can achieve very high purities only when palladium membranes are used. In terms of recovery, PSA systems usually find it difficult to exceed 92% recovery, while cryogenic processes can also achieve recoveries close to 99%. A key advantage of PSA is that impurities such as CO, CO2, H2S, and nitrogen are readily removed by adsorbents and therefore pose minimal operational issues. Cryogenic processes, however, are more vulnerable to these contaminants. H2S freezes near minus 60 Celsius degree and CO2 at lower temperatures, both of which can disrupt operation. H2S also presents risk of corrosion and equipment damage, while CO can poison or deactivate catalysts. Given that CO has an extremely low boiling point of about minus 190 Celsius degree, cryogenic systems commonly employ methane wash technique to dissolve and remove both CO and CO2. Overall, the PSA method offers greater flexibility than the other methods, and as we have seen, does not require any pre-treatment. Here you can see some examples of industrial hydrogen purification plants licensed by different licensors. As you can see, these plants commonly use zeolite 5A and activated carbon as adsorbents, and the number of beds can range from as few as 4 to 10 or more. The feed gases come from various sources. For example, one plant may use SMR off gas while another use refinery off gas, and they operate at different pressures with varying levels of purity and recovery. The hydrogen capacities also span a wide range from about 1,000 normal cubic meter per hour up to nearly 400,000 normal cubic meter per hour. This is the Linde hydrogen purification plant, which claims it can achieve purities of up to 99.99%. Their smaller units can process a few hundred normal cubic meter per hour, while their largest plants are capable of handling up to 400,000 normal cubic meter per hour. Now we want to look at the challenge that exists in simulating hydrogen purification systems using the PSA method, especially for industrial cases. First, adsorption systems are inherently dynamic and complex. This means that many PDEs and ODEs must be solved simultaneously, and the stiffness of the system adds to the difficulty. Some variables may change very quickly while others change slowly, making it challenging and time-consuming to solve the system. For instance, the pressure in the system may fluctuate suddenly, while the mass transfer rate of water may vary much more gradually. Another challenge is the variability of isotherms. For example, even with the same material such as zeolite 5A, the adsorption capacity can differ depending on whether it is produced by different companies or laboratories. In industrial systems, this variability can also appear over time. Adsorbents that have been in use for a long period may show different isotherm compared to when they were brand new. Here, it is recommended that you definitely perform the isotherm test on the system that will be used in the future, and use those IPs, or usually compare the data you get from literature with each other, and try to use the data that is more in line with the reality of your problem. Next is the kinetic data, mainly related to mass transfer coefficients or MTCs. As you've seen in the channel videos, breakthrough data, which is usually available in laboratory experiments, can be used to tune these values. In industrial cases, however, such data are often scarce, and because MTCs depend on parameters like flow rate and bed geometry, lab-scale values cannot be directly applied to industrial systems. Then, as mentioned, there is the computational cost, which usually requires running many cycles until the system reaches cyclic steady state, or CSS. Another important challenge is process optimization. This often requires intelligent algorithms, since there are many decision-making parameters and conflicting objectives that must be balanced. Such algorithms may need to run your Aspen adsorption model thousands or even tens of thousands of times, each time reaching steady state. As a result, it is often necessary to integrate Aspen adsorption with programming tools like MATLAB or Python. Pressure swing methods are typically classified into three techniques. The first is the usual PSA method, where adsorption occurs at high pressure and desorption at atmospheric pressure. In this case, whether or not you need a compressor depends on the feed source. If the feed already comes at high pressure, no compression is needed. Otherwise, you must compress it to achieve a higher adsorption capacity. The second is the VSA method, where adsorption takes place near atmospheric pressure and desorption occurs under vacuum. Since desorption is done under vacuum, a vacuum pump is required, and its energy consumption must be calculated, similar to how compressor energy is considered in PSA. The third method, often referred to as VPSA, combines both principles. Adsorption is carried out at high pressure, while desorption occurs compressors under vacuum. In this case, the energy demand of vacuum pump must be accounted for. And again, depending on whether the feed comes from a high or low pressure source, a compressor may or may not be necessary.